Thank you, Hank, and thanks also for the invitation to the organizers. It's always great to be back here at ESI. This is a wonderful place. And let me start by mentioning that this is joined with Dalia. Okay, and the topic is on the infinite horizon dispersing billiards. Okay, so I think this was the topic of some other talks Monday, but I was not around. So I don't know, and I don't know how you recall. So let me just start by mentioning what the system is. You have, for simplicity, let's just assume that you have a single scatterer. This is a circular disk on the torus. So this is the torus, and I don't know, here's the scatterer. There could be more scatterers than that. And the configurations in the phase space are points along the scatterer equipped with velocities, and I can make the following coordinates for that phase space, which I'm going to denote by M. These are pairs R and phi, such that R measures location with respect to arc length along the boundary of the scatterer. Okay. So R is just location along the scatterer, and phi is the outgoing angle, which is something that I can denote. Then I probably put this one here instead of there because I kind of blocked. So here's my configuration. I will denote this by omega. There's an R and a phi, which is the outgoing velocity measured by with respect to the normal at the point of impact, right? So many of you know this system. You also know that this system has, so I denote by T the billiard dynamics, which is defined as follows. If this point starts off from that point, then it proceeds along straight lines with unit speed. And then it enters on the other side of the scatterer, so we are just of the torus. So instead of continuing and ending up here, I just let it go, enter there, and there it's subject to an elastic reflection. And then this is going to be, by this is omega, this is going to be T of omega. So this is a self-map of this phase space to itself. This has the shape, phase space has the shape of a cylinder, right? Because this coordinate is cyclic, while this is just an interval. So, and this transformation is TMM. And there's also invariant measure, which when the scatter has this shape, so this is the unique, absolutely continuous invariant measure, and it is ergodic with respect to this transformation, which is not Lebesgue, but absolutely continuous with respect to Lebesgue, and the density is this cos phi. Okay, so I'm just mentioning this. Anytime I say that I have some probability or expectation, this is always understood with respect to this measure, right? Okay, and I will be interested in a particle observable for this dynamical system, which I'm going to denote by big X. This is vector valued, M to R, and this is just the displacement, but on the plane. So for omega, this is X omega, right? Okay. And with this notation, I will also introduce X I, which is going to be X at Ti, and this is a stationary sequence with respect to this measure of random variables, right? Okay, so this is a stationary sequence of random variables, and what characterizes this random variable, this R2 valued random variable, that this is not in L2, it's unbounded for this configuration, and that's related to corridors. So possibilities of arbitrarily long flight lengths. You see, if you just think about it extending to the plane, you will see that along this infinite stripe, which is free of scatters, the particle can go arbitrarily far. And in fact, in case we have infinite horizon, in the two-dimensional case, if you have infinite horizon, then it's not in L2. And this is related to the presence of these corridors. So what you need is that your scatterers are strictly dispersing, strictly convex, and sufficiently smooth observables, curvature greater than 0 everywhere, then it's not in L2, and then it has a very specific distribution, which can be computed. In fact, okay, let me also mention kappa, which is the discrete free flight. There's a very natural discretization when I just count how much I traveled in the Z2 lattice from the starting position, right? I'm mostly focusing on the true free flight, which is R2 value, but I mentioned kappa, mostly for specifying what sort of distribution it has. So it can grow along these corridors, and it has that sort of distribution, right? For large k, right? For large values of k, the chance that it is exactly, it takes exactly a large value k is proportional to 1 over k cubed. So in other words, this means asymptotic equality, right? This symbol. So this means that the two quantities are in 1 plus little o1 relation with respect to each other. And this also implies that the chance that x is greater than r, this scales as some other constant. Maybe I can relate the two, but I don't want, c2 over k squared. So this implies that this is not in L2, but just slightly not in L2, right? This in L1, that's in LP for every p less than 2, right? Okay, so in fact, this is in the non-standard domain of attraction of the normal law, right? So quite much is known about this billiard, but I think which gave a very big kick for the progress of this field is the result by Doma and Tamás Varjú on a non-standard limit law for this billiard. So if I just let Sn, the sum on I from 0 to n minus 1 xi, just think about what it is. It is the position of the particle on the plane after n iterations. So if you want to regard this as some sort of model of diffusion or Brownian motion, this is a very relevant quantity. So the result by SAS and Varyu from 2007 is that Sn over, and here I do not put square root of n. One of the organizers is the magician of colored chalk, Roland. So I follow his, well, I try to follow his expertise. I'm not going to make it, but there's an additional log n, which means that this is in the non-standard domain of attraction of the normal law. So this converges in distribution. So in distribution with respect to the starting mu to normal 0 sigma squared. And this sigma squared is again, let me mention that all these C2, C1, and sigma squared are explicitly determined. Okay, so these are very specifically determined by the corridor structure, the geometry of the corridors. What sort of corridors you have, what is their width, and such like. So they have a very explicit, they are not determined by some sort of Green-Kubo formula, but they are very exactly determined. Right? Okay. That's in dimension 2. Yeah, it's important. In dimension 3, we do not really have results. That's a matrix. That's a covariance matrix. Yes, it's important to point out. This is covariance matrix. And let me tell you what it is, actually. You can also relate it to the C2 and C1. In fact, if you truncate X at some level R, so this upper index R will denote truncation. Also, so this is X times restriction to X less than R, or less than equal anyway. Then the covariance of this truncated guy, okay, the X itself doesn't have a finite covariance, but the truncated does have, and it scales as sigma squared, okay? This is a covariance, again, this is a matrix. Covariance matrix. This is a vector. This is the scaling, right? Again, up to leading factor. Okay, this means actually, if you look at this limit law, that this is as if these were independent, identically distributed random variables with that sort of limit behavior, right? So now there are many refinements of this result by Doma and Tamás Varjú. It is an active research field, lots of interesting works about refining this, basically, understanding the process on the full plane, making corrections, understanding correction terms, and so on and so forth. This is exciting, and I do not want to list them because it would take too much time. There's one aspect, nonetheless, which haven't been studied yet, and this is the question of the almost sure invariance principle and the law of iterated logarithm. So this is for almost sure invariance principle and law of iterated logarithm. And let me mention what I mean by that. Yeah, maybe I mentioned some convention. Instead of log R, I will sometimes just write big L R. This is common in the probability literature. And this is the max of 1 and log R, right? So just to avoid negative or 0 values, right? Because we will iterate it quite many times, right? As people do it with logarithm, in probability. While if I write little l of R, this is just a slowly varying function. It can be anything. So this denotes slowly varying function, which has the property that L at lambda r over L at r tends to 1 as lambda goes to infinity. So think of something like logarithm or log or something like that, which tends to infinity as r goes to infinity, right? So this is this type of function. Okay, I just wanted to mention. Okay, so almost shear invariant is a law of iterated logarithm, right? So what do I mean by that? By almost shear invariance principle, I mean that if Wn denotes standard Brownian motion, at integer times, I could just as well talk about sums of independent standard normals, right? Then show or show that maybe on an enlarged probability space, right? Sn is close to Brownian motion, right? And here I put some covariance matrix, asymptotic covariance matrix sigma, and I use again Lorentz technology, because maybe in the standard normal case, there's just one covariance matrix. In our case, it's not going to be just one covariance matrix. It's going to be something that depends on n that you have to put here, right? That this discrepancy is little o of Cn for some Cn tending to infinity, and you want something tending to infinity as low as possible. You want to make it as close to Brownian motion as possible. And then you talk about almost sure invariance principle with rate Cn, and this happens almost surely. So you realize the true process and Brownian motion simultaneously, maybe on an enlarged space, such that you have such a closeness, right? And then what is law of iterated logarithm? This is that by law of iterated logarithm, I mean that Sn over some other sequence C hat of n is scaled in such a way that the limit is neither infinity nor 0, right? So in the sense of lim sup. So this is lim sup as n goes to infinity is equal to some a, where a is between 0 and infinity strictly, right? Okay, so in case we have just the usual sigma here, and Cn is sufficiently small, tends to infinity sufficiently small, that then maybe I should have written it this way, that I put C hat n for the more general situation, because we know what it is. This is the law of iterated logarithm, that you have to rescale not by square root of n, but square root of n times log n. This is the law of iterated logarithm, right? Okay. But maybe we have to modify our setting in this non-standard domain. Okay, so let me talk a little bit about the history of almost sure invariance and its law of iterated logarithm. Effectively, that Wn over square root of n log n, I think I have to put a 2 here. This is again understood almost surely. This is equal to 1. This is the Kolmogorov-Hinchin law of iterated logarithm, which I just realized is kind of 100 years old. So it's interesting. So this is No, that's not how you write it in English. This way? Okay. So this is from the 20s, right? And there was then Strassen, who proved the first almost sure invariance principle, assuming that the variable, okay, let me switch, if I will remember, instead of x to eta, to emphasize that this time eta is something which is not my initial x. Actually, let me specify that first I discuss the IID case and R valued. Okay, so this is what was first understood. Simply R valued random variables and under additional assumption that it has a force moment, Strassen proved the first almost sure invariance principle, and with rate, which was kind of 1/4 of n times something slowly varying, so some logarithmic corrections. And you see this was also something that implied the law of iterated logarithm, right? Because if it's sufficiently close to the Brownian motion, then you get the same scaling as for Brownian motion, right? Okay. Now, this was a very active field in probability, and the breakthrough and the strongest result is due to three Hungarian authors, KMT, Komlos, Major, Tusnadi. So this was something in the 60s, but this is something in the 70s, right? Where they proved the following. If x eta has finite moment generating function, then they could prove for the IID case, okay, with rate big O log n, right? Which is very strong. So it's stronger, it's logarithmic, it's an extremely strong closeness, and this is actually an optimal bound. So it can be shown that no better bound exists in the sense that you can construct counter examples. And at the same time, let me mention that if eta is in LP, then they proved rate, which was kind of n1 over p, and that's for p greater than 2, right? So if you know less, you just know that the variable is in LP, you get wrong reverse rates, but still it's getting better and better with improving the regularity of the observable. Then there's also a paper by Major, roughly the same time, which shows that if eta is in L2, but eta is not in LP for any p greater than 2, then the rate is little o square root of n log log n. So this is still sufficient to imply the law of iterated logarithm, right? This is in the standard domain of attraction of the normal law. Yet again, in a sense, this is an optimal rate. So for any function, any rate larger than square root of n log log n, he can create an example, which is in L2, but that far from the standard Brownian motion. Yeah? Okay. So after all these attempts on the IID case, there was strong activity to extend this to higher dimensions and dependent situations, and I'm not entering this. Let me switch to dynamical systems. I could mention several authors who contributed to this: Philip, Stout, Zaitsev, other Hungarian mathematicians. In dynamics, the first major robust results are due to Matt and Ian Melbourne, I think, around 2006 and 2009 for scalar valued and all vector valued cases respectively, right? These are also rates which depend on p. I do not remember exactly what they are. These results used Young-Tarr construction and martingale approximation, basically, right? And a very important paper, again, I'm not listing everything, right? Which is very important for us, is Guezel from 2010, which used with spectral methods. So with spectral methods, using perturbed transfer operators, he could prove ASIP. Basically, the result was that if eta is RD valued, so it can be vector valued, and eta is in LP for p greater than 2, again, we're in the standard domain of attraction of the normal law, then he proved ASIP with rate n to the lambda, where lambda is 1/4 plus 1/4p minus 4, right? So it's getting better and better with p, but it is just Strassen's rate, what he gets in the normal situation. Okay, so I mentioned this paper because our work also builds much on Guezel's approach by adapting. The dynamics is something that has a spectral picture. So you need, you know, two Banach spaces, weak space, strong space, and a decorrelation. Okay, it's a bit technical question. What you need is a sort of decorrelation formulated in terms of the characteristic functions of the variables, and this is very convenient to formulate in terms of spectral techniques. This is it, right? Okay, this is Guezel's technique, and this turned out to be very flexible. So it has a lot of further developments, this work. This is not the best achieved. I mentioned several authors which worked on this and still work on this in various combinations. Künyi, Dedeker, Korepanov, and Merleved. They have several papers. One of them is still not accepted. It's on the archive, but you can find. And basically, they regain Kolmos-Major-Tusnádi almost for systems with Young-Tarrs. So this is ongoing work, right? Again, I do not aim for completeness in citing the literature. But let me go to IID with non-standard domain of attraction, right? So we are in this case, in the case of the Lorentz case. So think of exactly the same situation. It could be somewhat more general, but for the moment, assume this, right? So eta RD valued, and as in the infinite horizon Lorentz case, okay? Same type of distribution. And the result is by einmal Again, this is several papers with some of them with co-authors, and this is around 2005 to 2010, right? So what is the result? I think I need my notes so that I recall it properly, right? Again, covariance of eta r, the truncated variable, behaves as 2 sigma squared log r, a logarithmic blow-up of the variance, the same type of within the non-standard domain of attraction, but IID, right? And in this case, let me give some definition. I will say that Cn is good, right? The rate is good if this is summable, right? So if the tail probabilities are summable with respect to Cn. So some examples of good Cn. First, I give you something which is not good. So it's basically 1 over the square of the rate. So this is diverging, right? However, if I put, I switch to Cn squared because I don't want to write that many square roots. If I have an n log n, log n, this is still not enough. But if I put here a gamma, where gamma is greater than 1, yeah, this is already good, right? Okay, for that you already have some ability, right? Okay, so this is good. And let me mention another one which is good, right? Cn hat, right? Squared. This is n log n log n, 1 plus log n sine squared log n. Okay, this is good. Okay. So, what Strasson's results prove that if Cn is good, then let gamma n squared, a truncated covariance matrix, be the covariance matrix of eta truncated at Cn, right? Okay, so this is the truncated covariance matrix. And this is, if you think about it, these Cn's that I'm mentioning have leading term square root of n, right? So in leading order, this would be something like sigma squared log n, right? Okay, because the 2 is canceled by the square root, right? Okay. Okay, and in that case, we have that Sn minus gamma n Wn, again, Wn is standard Brownian motion, is little o of Cn, right? Almost surely. Okay, so this sort of invariance principle. Okay, notice, in fact, which is a peculiarity of this feature, that Cn cannot go down to square root of 1 log n, which is in the limit law, right? So this does not imply the limit law, right? Okay, but it does imply the generalized law of iterated logarithm. So I will call this generalized almost sure invariance principle. And lim sup, as n goes to infinity, Sn over C hat n is some a which is between 0 and infinity for this C hat n. So this is the rate in the law of iterated logarithm, right? In this generalized setting. This is what replaces the usual square root of n log n. Yeah, that's important. So throughout, I use this density, right? In fact, maybe I can add this. Maybe I can add this, how this Cn comes about. For Cn, we have that any good Cn, we have that this A, right, is the supremum on those B's where sum on n from 1 to infinity, 1 over n, e to the minus bn squared cn squared over 2n acn. What is acn? acn is truncated second moment, right? So it's basically e of x cn squared, right? So this is converging, right? Okay, so this is the generic thing. And in case Cn and Acn are S with this density, right? Then you will get that this thing is going to be finite and positive, right? Why I'm writing it is up, it's awful, I know. Why I'm writing is up that basically, again, you just need to understand the asymptotic growth of this, right? If you think about from your probability course how the law of iterated logarithm was proved, right? You basically study Brownian motion, sums of Gaussians, right? Or Gaussians with a certainly growing variance, right? And actually you split it up into kind of geometrically growing blocks, use some kind of reflection principle within the blocks, and use Borel-Cantelli. So this is how the law of iterated logarithm is proved. By the way, I found a very nice lecture note by Ron Peled on the internet for the law of iterated logarithm. And basically, this is just a mimic of this argument with gamma and R, right? So this is how you get it. Okay. So now I think I can state our result. Sorry? It's B. Very good, from the back row. So, am I supposed to do this? I was looking forward to that, really. No, I do not want to spoil anyone's game. Yes, why not? So, our result in the infinite horizon Lorentz case, we can essentially regain this. Okay. I will say that Cn is very good if it is good. Okay, and on top of that, we have another summability condition. So it's C at 2 to the n squared, right, in the denominator, and I have a 2 to the n here, and a log n here. This is summable, right? Okay. So notice, comment, I may comment on this later. the Cn hat, the specific with the log and the Cn squared is very good, right? Okay, so we can prove the almost sure invariance principle with such very good guys, okay, right? So for the infinite horizon Lorentz gaze, we have ASIP, in this sense, generalized ASIP for very good Cn. So this is theorem, myself and Dalia. Yeah? Okay. So this is something we have recently completed and we'll put on the archive soon. Right? Okay, let's explain a little bit on this very good condition. Not just that. Yeah, so generalized law of iterated logarithm holds for Cn hat, right? So in particular, because this Cn hat we include among very good sequences, we have the law of iterated, this generalized law of iterated logarithm for the infinite horizon Lorentz gas. Right? Okay, so the Cn's that we study, I start with n log n, right? The Cn squared, square root of n log n, and think of something like that, where we have an additional correction term, L1n, which is where L1n is slowly varying. This is big O, right? This is the same as big O. So it's between log n and log n to some gamma with gamma greater than 1, right? So if you restrict to such sequences, yes? No, in fact, yeah. Thank you. Yeah, yeah. It's in a non-generate case, it applies to the components, but let's just state it this way, right? Basically, A is the largest eigenvalue of the covariance matrix, or something like that, right? You can find it explicitly, but yeah, thank you, yeah. So if you think of something like that, right, then what does this condition reduce to? Yeah, then C of 2 to the n squared is going to be 2 to the n, log n is going to be like n, so asymptotically equal to that in the sense that one is big O of the other, right? Okay, and you have an L1 2 to the n, right? Okay, and then this condition will reduce to, this condition will reduce to sum on n from 1 to infinity. 2 to the n cancels. You will have a log n on top, and n, and then L1 of 2 to the n, right? And L1 of 2 to the n is then between log n and log n to the gamma, right? So this way, the condition may look a little more tractable, right? Because this is some power of the logarithm of n, higher than 1, and then this is apparently summable. And you can check it also for this example. So in case of the Cn cubed, this is my L1n, right? And in that case, this summability will reduce to the integral, I don't know, from 1000 to infinity, right, of the following type, right? So you just use x is n log n, right? Sorry, log, x is log n. And then from this integral, the n log n will cancel, right, after the substitution, and you will reduce to something like that. And the finiteness of the convergence of this integral can be explicitly shown, right? Okay. So this is the result. And in the remaining 10 minutes, I do not have that much time, but let me comment a little bit on the proof of this result. Basically, not surprising that the first thing is to truncate, right? Namely, what we do that for I, which is between 2 to the n and 2 to the n plus 1, right? So the truncation is at time I. So we truncate the same way in these logarithmic exponentially growing blocks is with c at 2 to the n. So this is what we do. Here's a real line. And between 2n and 2 to the n plus 1, in this block, we truncate according to this index, right? At c at 2 to the n, right? At this level, right? So then just a simple Borel counter shows that considering this truncated yi instead of the xi makes an error which is tolerable, right? Just Borel counter argument. That's where the good summability is used. This is just the good summability. The very good is used at a more technical level, right? Okay. Then we use essentially Guezel. We adapt Guezel's approach. So Guezel worked for LP, right? I mentioned. So he has results in the LP case. After truncations are variables in LP for any p, right? Specifically, we work in L4. Okay, with the truncated variables in L4. Was it this one? Okay, and what you need for that, and this is the main, probably the main technical contribution that we make, is a good control on the truncated force moment, right? So the question is how the truncated force moment behaves. So second step, adapt Guezel's argument. Of course, this involves a lot of technical steps with p equals 4 and need control on E sum on I from 0 to m minus 1, so up to time n, of x I r to the 4. Okay, so how this force moment behaves, right? And what we get is that this we can control up to constants as m times r squared, right? Under the following conditions, if letting both m and r is truncation level, m is number of terms, both of them I let go to infinity, and we have that m is between r to some t1 and r to some t to the minus t2 for some exponents, right? So if you let m and r, number of terms and truncation, go to infinity, right? And you can obtain, under these conditions, we can get such a control, right? So let me tell you why this is natural first. First of all, you think when m is around 2 to the n, our truncation level is c of 2 to the n, right? Which is roughly square root of 2 to the n, right? So this kind of control is realistic. Actually, what we do, following Guezel, that in these stretches of length 2 to the n, we introduce small and large blocks, right? This is a classical technique in probability. And in the large blocks, which are less than 2 to the n long, we apply these bounds, right? And why this is remarkable is that, notice that if I just consider a single term truncated at level 4, this is going to behave how? This is going to behave like I from 1 to r, because I truncated level r to the 4, and the probability of x taking value I to the 4, sorry, was I to the minus 3, right? So basically, you just add up I from 0 to r, you get something like r squared, right? So just a single term has a force moment growing as r squared. So this is the optimal thing, right? No logarithmic corrections, right? You just add up the individual force moments in leading order, that's what you get. So this is the best you can get, right? And it's very important for us, there are no logarithmic corrections to that. Actually, Chernov and Dolgopyat in the paper from 2009 had already something like that, but it involved some logarithmic corrections, right? And this one we can eliminate. And initially, when we worked with these logarithmic corrections present, then it didn't work, right? So at some point of the proof, the absence of these logarithmic corrections was really crucial, that we could get rid of them. Yes? Okay, yes? Basically, yes. Basically, yes. So I do not have the time for that, but let me just say a couple of words. People who worked on this, for example, Hong Kong, will know very well, or Doma, will know very well what I'm talking about. In the infinite horizon Lorentz case, the variance of this x blows up, right? Yet, if you consider for any s greater than 1, this is already finite. Yeah? This is by decay of correlations. So you have exponential decay of correlations, but not just in an asymptotic sense. You already have exponential decay of correlations already for the first iterate, right? And that's because in the phase space, the sets where you have large values of x are very long stripes, much longer in the stable direction than they are in the unstable direction. And when you iterate them, these dimensions swap. And this way you can control the intersections. And that's why you get such a decay. So we rely strongly on this fact, yeah, and analyze this to the level of higher moments and so on and so forth, right? And that's how you get this one, which we plug into Guezel, applying the LP techniques there, but adapting them. There are lots of technical details which I'm not mentioning, but basically this is it. So it's decay of correlations, but not just in an asymptotic sense. It's also for any time shift you have already a substantial suppress of correlations. Yeah? Okay, so I think I stop there. Thank you for your attention.